Welcome everybody to the seminar. Non-standard time, but we're happy to have Madhu, our winter migratory. He comes here every year, so it's not winter anymore. This time in Bombay, we have Madhu talk to us about improved PIR schemes using matching vectors. Huh? That's cold as it gets.
At least it's winter in this room.
3 days ago.
Yeah.
Okay,
great. So thanks, Prahlad, and thanks to all of you for coming. So this is joint work with Fateh Hasimi, who's this awesome student of Swastik Goparthi, who was an awesome student of mine. Actually, most of the work was done by them. I just asked them questions and they found good answers. So I'll try to explain to you what we asked, what they found. So there are two objects of interest in this talk today: a private information retrieval scheme, which I'll define on this slide, and then a locally decodable code, which is very closely related, but it's not exactly the same concept. So we will keep talking about both of them. In a private information retrieval scheme, you're thinking of some database which is k bits long. Capital K is going to be at least one thing that I think will be constant through the talk, will be the length of the message or length of the database. And there are L different servers who each hold a copy of this database. We are allowed to ask them questions about this data. And your eventual goal is to recover some particular bit. Say the ith bit is what you want to recover. So the user wants to recover the ith bit. So it should send at most C bits to each of the servers. Servers each respond with at most C bits back. At the end, you should be able to compute f of I. The security, the part that's making it private, is that you would like the distribution of questions that you ask to any one server be completely independent of this index I. So whether you want I or J or K, should always get exactly the same distribution of messages. Okay. So each server on its own does not know what you're interested in. That's why it's private. And you're retrieving f of I, so that's why it's information retrieval. Okay. Does it make sense?
Non-adaptive?
Yes, we are only considering non-adaptive schemes. So user sends basically one C-bit string to the server, to each server, and each server comes back with one C-bit string. You could indeed ask adaptive versions, but we don't consider this. And this talk is about constructing schemes, not lower bounds. So these are good, useful if it's the case. Now, the related concept that I mentioned is a locally decodable code. For me, a code today, it's best to think of it as a function which takes k bits of information, 0, 1 to the k, very similar to the k bits in the previous information. You can think of that as some sort of a message that's being encoded by the servers. It's going to be encoded as n letters over some alphabet sigma, and today sigma can be pretty large. So we want that it need not be bits, it could be something much larger. And an L query locally decodable code. The number L in this slide and the previous one are the same, but they have different ways of thinking about it, is a setting where we say that, look, here's the encoding of the message. It's sigma, it's n bits long or n letters long. You get to query some L portions of this object. And based on these L objects queries, you should be able to recover the ith bit of the message once again. So you're interested in the ith bit of the message, and you should be able to ask this question. Why is this considered an error correcting code? In what sense is it an error correcting code? We will make a very strong requirement, which will imply that this will actually also be a good error correcting code. The strong requirement is any one of these queries, if you look at it, its distribution should be independent of what location, the index I that I'm interested in. Okay. Why is this interesting? So assume this is the uniform distribution on the whole code word. So for each location I that I care about, the location that I'm asking over here is uniformly distributed. If that's the case, an adversary who's choosing to corrupt a small fraction, epsilon fraction, will not really be able to hit the location that I'm going to actually query. The probability that any one of these queries will be hitting this one, the error location is epsilon. Probability that there exists a location that's corrupted that I actually query is L times epsilon. And if L epsilon is small enough, then we will actually recover the original f of I correctly. Okay, so this is what a locally decodable code is. Any questions about this? Yeah.
There, the message was only one of k possible k capital K possibilities, or the previous slide was it 0, 1 to the k, or in the PIR scheme?
So the portion that's similar in both of them is that we are interested in only one bit of the message.
Okay.
And that index is always going to be I, or
Okay.
at least in these two slides has been I.
Mhm.
And the message is the entire database that we are thinking of. So 0, 1 to the k, so a k-bit string is the database initially.
Yeah, no, because the previous one, it was.
So yeah,
Oh,
the message
the
is,
database is FK.
yeah, the message is a function from k to 0, 1, or
Right.
it's an element of 0, 1 to the k.
Okay.
Good. Sorry, yeah.
Is sigma just n?
Is sigma just n? Sigma in our applications is going to be actually much larger than, the size of sigma will be larger than n, and log of sigma is what we will really care about. Which is exactly. So actually, you're right. I think in many of our applications, sigma and n will be comparable in size, maybe maybe polynomially related in each other and so on. Log sigma and log, and I don't remember. Okay, log sigma and log n will be polynomially related in each other. Why is it interesting? So if you had a locally decodable code which takes k bits and maps it to sigma to the n, and is L locally decodable, you make L queries, that implies that there is an L server private information retrieval scheme. What's your question? Well, the queries that you make are all questions. So you send log n bits to each server saying, give me the jth bit of the alphabet, give me the kth bit of the encoding, give me the kth bit of the encoding, etc. And so each time you're sending log n bits. And what do they respond with? They respond with an element of sigma, so which they are responding with log sigma bits. So the communication is maximum of log n and log sigma. So private information retrieval schemes, in other words, are locally decodable codes over pretty large alphabets. Okay, and that's the way to think about this. But we've been interested in locally decodable codes independently for a while, and the technology got pretty good with that. And today we'll be trying to see how to use this large alphabet option to get slightly smaller amounts of communication. Okay, so the oldest private information retrieval scheme, as well as locally decodable code, they've all been based on the concept of a multivariate polynomial. In this setting, so let's start by looking at this portion of the screen right now. So we fixed some finite field, which is there will be some integer which will denote the number of variables. We will decide to take our information and represent it as the values of some partial function over a set. This what I'm calling T. I think T mentally looks like a triangle to me. It's a simplex of some sort in m dimensions, but it doesn't matter what the set exactly is. The important thing is that this is a set of points where I can specify a function such that I can always extend it to a degree R polynomial over the entire space based on this. Okay, so I start with some function, an R variate polynomial. I pick a set of points which are somehow linearly independent, where this polynomial can take arbitrary values. This portion of the information is the message. Its encoding is the evaluation of this polynomial everywhere. Okay. So this will give me a function. So I start with a function. This is the message. It's mapped from this interpolating set T. And because my information is always bits 0 or 1, which are elements of every field, I just take a function from, I can take any function from T to 0, 1, encode it as a degree, think of it as a degree R polynomial. That R polynomial, so that polynomial agrees with this function at this point, and then you just evaluate it on all the points in the domain. Okay. If you do this, you get a way of representing the original information. The information was function values over a small set. The encoding is function values over the entire set. This is making it redundant, so you get extra information. And now this is actually locally decodable. How do you decode it locally? Well, what does it mean to decode this function locally? I'll give you some point in the triangle and say, look, what is the value of f at this point? Which is equivalently, what is the value of this polynomial p at that point? Now, I don't want to ask this one point because that would be revealing the query that I have in mind. Instead, I'll pick some random point on the space and draw the line through the point that I'm interested in and this random point. I can query any one of these other points, and these are all individually random. If I ask r plus 1 queries on this line, that gives me enough information to decode the function value on this entire line, and that will in turn give me enough value to recover the function value at this point. Okay, does this make sense? So as soon as you work with multivariate polynomials, you somehow get this ability that I can encode a lot of information because I have lots of variables. When I want to decode, I'm only working with a univariate function because I'll pick one line, and on that one line, as a function, the parameter describing the line, the multivariate function becomes a univariate function. And univariate functions are easy to decode. So this is the canonical way of converting, getting a private information retrieval scheme or a locally decodable code. What kind of parameters can we get? We need to work with a field of size at least r plus 2. We just go through these things. There were r plus 1 points that I wanted to pick, but none of them could be the point that I wanted to query on this line. So it must be at least r plus 2. You can, let's say we managed to find a field size which is exactly r plus 2. The query complexity will be exactly r plus 1 or the field size minus 1. And the length of the message is the number of points at which, how many coefficients does a multivariate polynomial of degree r have, m-variate polynomial. Number of coefficients that a multivariate polynomial of degree r has is roughly m over r to the r. R is going to be, did I mean that? That is correct. Okay, sorry. So R is going to be a constant for most of the things. We don't want to make too many queries. We're thinking of constant number of servers. So we'll think about R, for example, as 3, R plus 1 is 3. So R is 2 in this example. When you use R equal to 2, you're making roughly, you get to, if you're working with m variables, you're looking at degree 2 polynomials. There are roughly m squared coefficients that you can think about. And the number of evaluations, on the other hand, is the Q, the field size to the m. So relative to the length of the code, which is k, the number of bits of the message, k is m squared. So the length of the code n is like 2 to the root k. 2 to the m, or constant to the m, exponential in m, and that's to the root k. So if you work with those parameters, you get something like a 3-query PIR scheme, which takes k bits and has communication complexity square root of k. This might not sound great, but this was the first PIR schemes that we knew, and this is sort of reasonable. Now, if you look at this scheme, we are not really balancing the length of the information that I'm sending out to the from the server to the receiver, and looking at the amount back. The query sizes were pretty large. The answer sizes were just bits. They were like each one of these servers was sending one field element, just kind of tiny amount. So it wasn't great, but this is the best that we could do.
Wouldn't it have just been like, if I was going to ask a very large query and receiving a very small answer, can't I sort of say I will make my query shorter and I just expect the server to give me answers for all extensions, etc.?
Exactly. So there are very good ways of balancing this trade-off, to making this trade-off better. In fact, one of the nice ways that was described in in an early paper was we said you could just take your message of length k, think of it as k to the 1/3 chunks of length k to the 2/3. play this game with each chunk of size k to the 2/3, but the query to each one you make the same. Okay. So, and this somehow was already giving us some improvement, I think. Maybe I'm not doing it in the best way, but you can get some improvement this way. I mean, you are interested, sorry, you're only interested in one of these chunks, but you don't have to say which chunk I'm interested in. You just play the same game, pretend you're going to ask for the same bit of every chunk. Okay. So that gives us some improvements already. There was a very nice algebraic way of balancing this trade-off. And this is something that's going to be important for the rest of the talk. So let me tell you about it. This is what's called the derivative codes of Woodruff and Ekhanen. They said, look, there's different ways of balancing how much information I'm sending to the server and how much the server is sending back to me. Here is one good way of doing it. From now on, I will think of the information as not just being encoded by its evaluations of this polynomial, but also evaluations of the derivatives of this polynomial. So what does a private information retrieval scheme along this lines look like? Anytime I want to ask a server a question, I'll ask them not only what is the value of the function at this point, but also give me all its partial derivatives of some order at this point. So let's take a very simple case. I'll ask you for all the partial derivatives in each direction. X1, x2, x3, and so on to x sub m. There are m directions. Give me the partial derivatives in all the m directions. Now, each server responds with roughly m symbols from this finite field. My query is also m symbols from this finite field. I have to specify a point. So the query length and the answer length are balanced. And what does it buy me? Well, I don't need, in order to decode a function of degree r, I only need r over 2 evaluations and derivatives. Okay, so if I give you the derivative in all directions, in particular, I can use calculus to compute the derivative in the direction of the line. Now I have the value of the function and its derivative at r over 2 points. That's enough to recover the value of the function everywhere, and now interpolate. This balances things very nicely, and I think improves the communication to k to the 1/3 in both directions. There were simpler ways of achieving k to the 1/3 in this case, but this certainly achieves it. And this is a scheme that clearly sort of generalizes nicely. If you have more servers, you increase the degree, and anytime you want to reduce the communication, you might be able to use extra derivatives. You can ask for all derivatives of second order, but that will be m squared things that people will be sending you. So you can do that, but there's a cost. It may be worth it, may make things better or may not. Okay, so you have to follow these numbers. So this was the state of the art in 2005. In particular, you could say, look, I'm happy with communication k to the epsilon for some epsilon. What can I do? Well, there will be some positive constant L such that L servers will get you to k to the epsilon communication. But you have to increase the number of servers in order to reduce the communication to k to the epsilon. And this was the best. So for every L, there was some epsilon saying, this is the smallest you can get communication to be. Anything lower than this, we don't know schemes. Does this make sense? So in the previous page, we had 3 servers getting k to the 1/3. Maybe you can go to, by the time the state of the art came along, 3 servers became k to the 1/5, but maybe not k to the 1/10. And there were similar epsilon L dependencies in all of the cases. Then in 2006 to 2008, there was a series of papers by Ekhanen, and then Raghavendra, and then Efremenko, that led to some amazing results. And they led to 3 query locally decodable codes. 3 queries and locally decodable codes, which means actually over a constant size alphabet, maybe even binary, I don't remember, where the communication complexity was less than any polynomial in k. So it was k to the little o of 1. Something like 2 to the square root of log k, those kinds of numbers we started seeing. Okay. I'll describe the scheme in greater detail. Yeah.
First result which you mentioned there, those parts, there was an absolute epsilon below which they could not go.
There was an absolute epsilon below which you could not go.
Yeah.
In fact, I mean, the initial behavior was k to the 1 over L plus 1 or minus 1. Okay. And then we really thought, oh, k to the 1 over L must be the right answer. And then there was a paper by, I think, Ishai and Kushilowitz and others, which said, oh, no, here's some other scheme which does better, which was actually significantly better. Then Woodruff and Yakanen came along and said, oh, at the very least, there is a sort of a sane scheme which gives you k to the 1 over 2L, and that's the derivatives.
Okay.
And 1 over 2L was the best we were able to do till now. And then
Even if you flip the order of coefficient, that is for all epsilon, there exists a L which is dependent on epsilon.
yeah, it's the same thing. I mean, if you specify the epsilon, there was some L at which we would be bottlenecked. Yeah. That would be a lower bound will be necessary in those days. So, of course, this was not an impossibility result. In particular, Ekhanen, Raghavendra, and Efremenko came with 3-query locally decodable code, which got communication to the square root of log k. And then another 10 years passed by before Dwyer and Gopi actually were able to build private information retrieval schemes out of it. So recall, private information retrieval is when we are allowing large alphabets, and to get back use this idea of large amounts of information took a good 10 years. And this is a pretty massive piece of work. It's very clever, but also has a lot of intricate details that you have to go through. So what's this talk? So I was going to put in something here, but apparently that's what I have. So I think, I thought about it and I said, look, I'll just go on with the story and keep telling you the thing. But roughly, what are we going to do in this talk? I'll give you our results, and then I'll tell you mainly, an easy way of getting to Yakanen's result, an easy way of getting to Dwyer Gopi result, and then some ideas that allow us to sort of now going from these good ways of getting those two results. Easy way to get to Yakanen, maybe not. That's very arguable. It's a sort of there's a certain part of the Yakanen result that I always trip over when I try to prove it. Finally, I think we have the proof which doesn't at least trip me over. And then I will try to tell you about our own results, but it's not. We may not get to that. We'll see. So the key to Yakanen and subsequent results is this concept of what I call matching matrix. I call this a matching matrix. People in the literature call it matching vector families. I will switch to vectors later, but for now, this is what a matching matrix is. The matrix that looks like this. So it's a k by n matrix. So it has some k rows and n columns, or maybe the other way around, whichever. I don't know what the convention is today. The properties of this matrix are, if you look at the top k by k part of this matrix, it looks like an identity matrix inverted. Okay, but it's inverted. What do I mean by inverted? Along the diagonals, you have zeros. Off diagonal, you must have entries which are non-zero. And these can be entries which are arbitrary non-zero values, but we will often require them to be special non-zero values that I'll call S star. So my notation S star will be some set S without zero in it. So that if you look at the top part of the matrix, all entries are from S, the diagonal is zero, and the non-diagonals are non-zero. And then the rest of the matrix, why do we need it? Well, I want this matrix to be closed under addition. So if you take any two rows and you add them, the resulting row should also be in the matrix itself. So it's a closed linear subspace, if you want to think of it that way, except entries of this matrix are not finite field elements necessarily. They can be elements of some arbitrary group, if you will, abelian group, but we'll take just cyclic groups Z sub M today. Okay? That's the kind of object that we are interested in.
The closure is only for the bottom or for the entire?
Any pair of rows that you pick in this matrix, its sum should also be another row in this matrix. Okay. Now, if you go by usual linear algebra thinking, suppose we really had identity 1 here and 0 here, and you want this whole thing to be closed under addition. Well, it's clear that the number of rows, if we are working over a field of size q, has to be q to the k. The amazing thing is, if you allow these entries to be, so firstly, Ekhanen already noticed that if we are working over a field of size Q, and these entries are 0 and these are non-zero, then the number of rows doesn't have to be really n to the k, it could be n to the k divided by q. I mean, sorry, it could be q to the k divided by q. So, yeah, in the exponent, but still, sorry. So you could possibly get something that looks like this, but even that's not going to be great for us. Okay.
What's Q here? Q equals to.
Sorry.
What's Q here?
If you're working over a field of size Q, then you could get matrices where n is roughly equal to this. Okay.
And here, in Ekhanen's case, it's actually field elements,
These are field elements,
not
things. So, and Ekhanen actually uses those field elements and builds very interesting codes out of those. But this is still not rocket science. The number of rows is really exponential in the number of columns. Not good. The brilliant step in Efremenko was to realize that, oh, there exists results in the literature which have already considered this question and seen that if you work over non-fields, if you work over Z sub m and m is composite, then can get n, which is 2 to the root log k, or better, depending on how many different primes divide m. Okay, so you can get, yeah. This is unconditional. Its implications to building codes became conditional because in order to use this, you actually needed some Mersenne primes and so on, and that made the things conditional. So, but this construction, this is actually quite simple and quite doable. And you can also, I mean, actually, you can very easily prove that this is the best possible. And once you see the proof of this is why this is the best possible, you can possibly unwrap it into one which says, oh, this is how you can also get this. Anyway, so that's these are the key objects of interest, and once we use them, we can get good codes. How do you get?
one.
Yeah.
Now that go back to Efremenko's construct. The Efremenko is going to put not a field element at every location, but he's going to put a member from the
Z sub m.
Z sub m.
Yeah.
Is there a construction in which you don't put a field element, Z sub m element, but actually an element from a vector space? That is, this is basically not just a matrix, but
multiple entries from thing. I don't think
as a tensor, and the number of tensors is smaller.
Good. So you could consider that. As far as I know, that's not going to buy you a lot. Okay, so as long as you're still living in this sort of a thing of fields and vectors over fields.
No, but these are not correlated tensors. No, so your base alphabet is no longer Q. It is, if you're giving T matrices, it's Q power T, and you don't have to have a separate. So these could be very.
Right. Okay. So I mean, so honestly, I don't know that. I haven't looked at it carefully, but I would suspect using vectors is not necessarily going to buy you much.
Okay.
I mean, at the end, this restriction that everything has to be closed under addition is going to hamper you.
Okay.
I mean, the thing is in going from, say, I mean, Z sub m, I mean, for m equal to 6, 2 times 3, you get massive improvements over here. Over here, if you decide to go work with F9 instead of F3, I think you might sort of get a savings of 2 or 3 or something in this thing. It's not going to be, as far as I can tell, it's not going to be a big improvement.
If you are putting elements of a vector space, you could instead put elements of a vector field extension.
Yeah.
Sometimes it's easier to get, I mean, we see lots of codes which are codes over vector spaces, but not codes over finite fields, and we haven't been able to convert them into
For
codes.
example, multiplicity codes, I can't think of it as this one. So question is, what's the multiplication operation over there?
Yeah. Okay, so let me include, yeah.
So in the previous thing, when we say that it has to be closed under addition,
Mhm.
we truly mean just addition, right?
Addition
Not
mod M.
linear not A times a row plus B times. Okay.
Just addition. There's no notion of a multiplication
Multiplication
at
that
all.
you have.
And at this stage, it's really just, yeah, additivity as in groups. Yeah. So now there's a second ingredient that I have to include, and then I can tell you what Ekanen and others' results was. This is what is called an S decoding polynomial. So recall that the matrix had this feature that the top part of the matrix was all entries of S. The top k by k entries were all from S. So here's what an S decoding polynomial is. So I have to give you the set S, which will be a subset of Z sub m today. And I'll also give you a finite field with an mth root of unity, primitive mth root of unity. So it has to be a special field. M has to divide Q minus 1, etc. So let's assume that we have it. So if you're working with M equal to 6, you can work with a field on 7 elements, and that's good. And now a polynomial P with coefficients from FQ is called an S decoding polynomial if it has two special features. P evaluated at 1 corresponds to, let's think of omega as the special nth root of unity, omega to the 0. So 0 is the special elements on the diagonal, omega to the 0, which is 1. P of 1 should be 1. But P of omega to the S should be 0 for all other entries. Okay. So this is the notion of an S decoding polynomial. And we'll say that a polynomial P is L sparse if it has only L non-zero coefficients. Okay. So here is the theorem of Ekanen, Raghavendra, Efremenko that tells you how to combine these two ingredients. Give me an S decoding matrix and give me an L sparse S S matching matrix and an S decoding polynomial. I'll give you a PIR scheme. What are its parameters? The number of servers that I need to work with is the sparsity of this polynomial that I have. And how big is this code going to be? It's going to map k elements to FQ to the, so to element, the alphabet will be FQ, and the length will be n, for where k and n were exactly the dimensions of this matching matrix. So this matrix basically translates entry by entry into the generator matrix. I just take every entry over here, A, and convert it to omega to the A, and that maps it from an element in Zn to an element of FQ. And now I have a matrix over FQ. This is the generator matrix of a private information, of a locally decodable code. Okay. Now, this is an absolutely beautiful proof. The part that usually trips me over is I have to go from this matching matrix. I mean, I can tell you what the code is very easily. Explaining what the decoding is going to take some time, and exploring why it works, etc., is going to take some time. And today we're going to short circuit some of those things.
So Madhu,
Yeah.
The previous construction which you gave actually yielded you locally correctable codes. This only is your locally decodable code.
Yes, and by the results of Kothari and Manohar, this is actually
Necessary.
its performance is better than that of any locally correctable code. Yeah. Okay. And notice that this is all going to be, at the end, we want to get 3 queries, but I'm very happy with getting constant number of queries and sub polynomial amount of communication. That would be pretty interesting, and we will get that. So Ekanen, like I said, actually used M was 2 to the t minus 1, and it was a prime. Well, these are the Mersenne primes, and we don't know of infinitely many of those. We believe that maybe, but we don't know.
Simplify multiple proofs.
Was that?
It will simplify multiple proofs.
It will simplify many proofs, but this one, it won't. By now, the theorem is moot. He used the set S, which was all the 2 to the 2 to the t minus. Sorry, these were entries of order t. So these are like tth roots of unity, I think. And he used the way he got a 3-query code out of it is to prove that this particular set S has a 3 sparse polynomial, which is 0 on this set. Okay. And so the entire construction of the matching matrix for Ekanen was kind of simple. The ingenious part came in this 3 sparse decoding thing, and that's where he got his great result out. Efremenko switched to m equal to 6. The set S that he worked with, these have to be subset of Z sub m, where just the entries 0, 1, 3, and 4. That turns out to be the collection of entries that gives you a pretty large thing. Now you want a polynomial which is going to vanish on 3 points, 1, 3, and 4, but not vanish on the 4th point, which is corresponding to 0. So you can find a degree 3 polynomial and it has 4 coefficients. So immediately looking at this thing, you get a 4 server or a 4 query locally decodable code out of Efremenko. However, he did some, I think some searches and managed to find a 3 sparse polynomial that worked for him. And so also got a 3 server result, 3 query result out of it. But nothing was 2 queries in this space. And two queries simply won't work in the setting. So, and then this was the state of the affairs. We had very good, we said, you can actually, with any constant number of, with some constant number of servers, in particular 3, can get subpolynomial communication. But if you wanted to go to 2 servers, nothing was known. To get there, Dwyer and Gopi got something in 2015. And it matches the same parameters as as the Efremenko construction, except Efremenko needed 3 servers and Dwyer and Gopi could do it with 2 servers. Now they used large communication in both directions. Okay, it was a great result. It was complicated, and I think so for me, this Dwyer Gopi is the fact that it's complicated and the fact that there was a sparsity in the Yekhanan Efremenko result. I mean, the paper really didn't know how to use something simple like the degree of a polynomial is low. They'll have to go from a degree of a polynomial is low to proving that sparsity is low as its degree should imply, and then use the sparsity to prove. I mean, if you have low degree polynomial, there should be a better way of using it. They didn't have it. So we will try to find that.
Did Dwyer Gopi use Efremenko?
Yes. Oh, Dwyer Gopi is taking Efremenko and putting it on steroids. I mean, it's really like, it actually combines the matching matrix method along with the derivatives method, something that we are also going to do. But in order to do it in a way that's somehow consistent with the fields, they were doing something really intricate and subtle. So it's like, it's a pretty impressive result, but it's not easy to explain. So what's our result? So we're going to get a new way to construct, to combine derivatives with matching matrix. And the implication roughly is whatever used to be something of the form, oh, here's a 2 to the R query, locally decodable code doing blah, blah, blah. We can now get a 2 to the R minus 1 query, 2 to the R minus 1 server PIR scheme doing the same thing. Same amount of communication, but now. In particular, I think we can also get a 2 server PIR scheme with 2 to the square root of log k things. And I would say that so when we got this proof, I was very happy with it. And then we saw a paper by, I'm sort of forgetting all the authors, but I know that Amos Beemal is one of the authors in this, 2 of the authors in this paper, who have an extremely, extremely simple 1-page construction and analysis of a PIR scheme for 2 server PIRs achieving the same parameters as Dwyer and Gopi. So ours is, I would concede that we are only the second simplest proof, but somehow their proof I haven't been able to internalize. I wanted to read it up well enough to present it, but I couldn't internalize. At least our proof I've been able to internalize.
So the Dwyer Gopi improvements also carry on for other larger number of servers, or some?
It does carry on, it does give improvements for
all.
larger number of servers. It doesn't do it for all. There are many servers for which they get improvements, or maybe not them directly, but other follow-up works gave it with their method. We are going to get actually improvements in all cases where they did not improve. And in the cases where they improved, we match the improved bounds. So essentially, this is the...
And that implication is a black box implication or certain type of
The things are in quotes because it's in quotes. Yes. No, that's not a theorem. That's roughly what happens. You'll see roughly what the theorem is. Morally, so there are lots of these things. What's the best S decoding polynomial you can get for this set S? There's no theorems which capture it. Sometimes there are good ones and sometimes there aren't. So what we are saying is, look, take these things, you would apply it to get, actually the right way to think of it is, if you took a scheme to use a certain number of servers, certain amount of communication, then you could get a smaller amount of communication with the same number of servers, is probably the best way to say that results. Okay, so again, reviewing Ekan and Flamenco, there's this matching matrix, but now I want to start thinking of it in terms of these matching vectors. So one way to think of this part of the matrix, the top part, is each row is indexed by some element u sub I, vector u sub I. Each column is indexed by some vector v sub I. And what I'm writing down there are the inner products of ui with vi. Inner products mod n. And so the inner products are 0 on the diagonal and are always elements of S. That's the general condition. But then if you do that, then you have to take basically because this should be closed under addition and so on. So all possible other vectors should have also been represented somewhere. So if ui and vj's are elements of zm to the L, then the total number of rows is going to be m to the L, because every m to the L vector, its inner product has to be represented somewhere in one of these rows. This is the right way to think about matching matrix constructions. This is how you'll construct matching matrices by designing these vectors ui and vj. And once you have this representation, the encoding will basically say, suppose I have k bits of information that I want to encode. You could just say, look, I'm going to multiply the generator resulting from this matching matrix. So the one where you put the omega to the mij is the ijth entry. Take that generator matrix and multiply it with this vector. That's encoding, that works. But in our view, it's better to look at this as if we are defining a multivariate function. Okay? F of x is an L bit vector, L variable vector of formal variables x1 to xl. I'm looking at this polynomial whose coefficients are m sub I, but the monomials are not necessarily all distinct. I mean, actually, they probably will be, but not all the monomials are being included. I consider the monomial x to the ui. What does x to the ui mean? X is L variables x1 to xl, and u is itself an L variate thing. So this is an L variate polynomial. Okay. L, notice, is going to be a number which is much smaller than k, hopefully, and smaller than n. Typically, I think L is like square root of k. Is that? No, maybe something else.
Capital N is m to the L, no?
Capital N is m to the L.
So L is like log n.
Yeah, maybe. So
M is constant in your.
Sorry?
M is constant, no?
M is constant, yeah. M6 is good for today.
Okay.
Yeah. Yeah. And so yeah, this is exponential in log k, square root of log k. So yeah, L should be like square root of log k. Okay, good. So we're looking at relatively small dimensional objects.
How should we think of those vectors in terms of the matrix? I missed that.
Sorry. So these vectors index the first k rows.
Oh, the index.
Those
the first
vectors index the first k columns, all the columns. And the remaining guys are now basically in the products of all vectors with VIs or all vectors with UIs.
Oh,
and I'm maybe
okay.
mixing U and V in the tradition of my student. So, yeah, so
Modular code, but you are only considering certain monomials.
this is like you could say this is like some sort of a multivariate code. So it's a read-muller code, but monomials are very carefully chosen. So it makes it, and then,
And the evaluation is also, because m divided q minus 1, the evaluation is on some grid sitting, some multiplicative group side.
Right. Sorry. Oh, this should not have been z sub m to the L. That doesn't make sense. Doesn't
Should
type
have
check.
been the- you
Should be
identify-
omega to the z sub m.
You
kind of thing.
identify that with the.
With
roots of
the
unity.
with the roots of unity. You should be really h sub m, which is going to be my notation for thing from now on. So h sub m to the L. H sub m are the mth roots of unity in F cube. Okay. So this is so I'm only evaluating it on small set of the field, but I mean, really m to z sub m to the L will be of size 6 to the L. And if the field was FQ was 7, then that's 7 to the L. So it's not a big savings over there, but this is the set that we care about. Now towards decoding, and this is where we start to depart from Ekanen already. So what are we going to do? We say, look, I mean, I'm not going to give you the decoder yet, it's in the next slide, but what's the idea for the decoding? Well, how am I doing on time? Don't see.
15 minutes.
15 minutes. Okay, sounds good. So we're going to pick this beta. Beta, ignore beta for now. This is just to make sure that my queries are going to be random, so on. Ignore it. What I'm really defining is some curve, C of t, which is of the form capital T. So it takes one variable and sends you into this L-dimensional space. Okay. And the jth coordinate of it is going to be t to the vi of j. So remember, you have this vector v sub I. I want to recover the ith coordinate. Okay. So in order to recover the ith coordinate, I mean, so far I have not used in this previous page. On this side, if you look at it, I have not looked at vi at all, but its presence should clearly be used somewhere. I'm going to use it now.
Just one picture, the UIs are indexing the rows or VIs are indexing?
It doesn't matter. Think of this, forget the matrix now.
Yeah, it's behind the rest.
So this is, I think, the best picture to use for this one. Okay. So what am I going to do? I'm going to say, look at t, which is a single formal variable, to the power of vi of j. Okay. So the vector vi has a jth coordinate, that's some integer. Raise it to the power of that integer. Okay. And this defines a new univariate function, g of t, which is just f. The function f is the database. Everything that I'm interested in is there. F of c of t is this quantity that I'm interested in. Okay. Now, this is a very high degree polynomial. Okay. But if you look at all of its coefficients, all the monomials, you're going to be looking at mi times x to the ui, and x is going to be some t to the vi. So what does it really going to look like? It's t to the ui vi. It's what this thing looks like. So this thing is of the form summation mi t to the mj vi uj. Okay, so this inner product is going to be what's sitting there. That's what this function looks like. Okay. Now, this is going to be as such a very high degree element. I mean, I'm not doing mod m. Okay, but we should do mod m. Might as well do mod m, because at the end I'm going to plug in for t roots of unity. And this is just going to be, doesn't matter what these numbers are. So you might as well do mod m. But the nice thing is, what happens when you do mod m? There are many of these coefficients that are all going to collapse into each other, but they're all happening on powers of t which are other than 0. There's only one thing that will give you a contribution to t to the 0, which is mi. Okay, so you're just looking at the coefficient of t to the 0 in this vector. So that's the key in this paper, the first key in this thing. So all we're looking at is g of t, which is this guy mod t to the m minus 1. This is clearly a low degree polynomial. I need to interpolate and find the value of this low degree polynomial so that I can recover the coefficient of t to the 0. How will I do it? I'll just ask the value of g of t everywhere. And here's where the beta being random, etc., comes in useful. All these queries are going into random places. These queries each give me the value of G at one point. I recover it from M places.
I guess, do you want to pick beta from H to the M rather than ZM?
Yeah, beta from H to the M. Sorry, again. Okay, correct. No, okay. It happened here notationally, it's fine.
So that's
Because
correct, because omega to the
yeah.
beta j.
Oh,
Yeah.
because I did the omega to the beta j, but you're right. It's the same as picking from H to the M randomly.
Random H to the M.
I just want something random in H. Okay, so that's the nice thing is this now explains completely why the Ekanen-Efremenko scheme gave you a constant query locally decodable code. It's not the best of parameters, but it at least gives you something reasonable. Now I'm going to go in the direction of, okay, so this is the full decoder, but I'll skip it because I think we just went over it.
So this gives you a 5 query.
This would give you maybe even 6 queries. I think you actually need M queries,
M queries.
because there's an M minus 1 degree polynomial. You
Okay.
take all the 6 roots of unity and do it. Okay. But it's constant query.
Yeah.
Okay. And we'll talk about that other thing briefly, hopefully. So, but before I go there, let me give you the Dwyer-Gopi result now. And this is actually where things get really, really fun. So here's what, the idea is we want to use derivatives to compute. So I don't want to make 6 queries for G. Instead, I want to make 2 queries and somehow recover G. Okay, this little G. How can I make 2 queries? Well, maybe I can ask for G of, some 2 points, G of +1, G of -1, or something like that. And then G prime and G double prime. If I can get 2 derivatives at each point, then I'm in very good shape. How can I get derivatives? And the useful identity that we do, and this is in order to get this identity, we work over a very special field. We are not going to work over a field with a 6th root of unity, but instead a field with a 2nd root of unity. Okay. And so the field in particular is going to be F3. Okay, wait, sorry, did I do this right? Yeah, okay, it's F3, okay. So what happens with F3? Well, I want to go modulo the polynomial z to the 6 minus 1 at some point. But z to the 6 minus 1 is the same as z squared minus 1 cubed, because this is, I don't know, Frobenius, whatnot. And what does it mean to say, I want to know the values of g of 1, g prime of 1, g of double prime of 1? It's like saying, give me g mod z minus 1 cubed, right? And give me g mod z plus 1 cubed. So these are legitimate questions I can ask by just, from one server, just say, look, at this point that you're interested in, I want this one thing. Why? Because I'm really interested in little g, but this also happens to be the same as capital G. This this big guy preserves this identity because of this condition. If it wasn't for this identity, I wouldn't have had this. So I can actually just compute, I can ask the servers to give me capital G and its derivatives at various points. The derivatives go in m different directions because capital G is back to being an m variant. This is going to be, I can't ask the server for capital G because I don't want to tell them what curve I'm interested in, but I can ask them for capital F and its derivatives at any point. Now I have to tell them, I can't afford to tell them which direction, so I just tell them in all possible directions. And that increases the amount of communication. Instead of being L, it's now L squared. So instead of being square root of log k, it's square root of log k squared. Sorry. Yeah. No, it works out in the right way. I think it's like exponential and 2 times square root of log k or something like that. Okay. So this gives me the, so it blows up communication relative to the Ekanen kind of schemes, maybe even relative to Efremenko by a polynomial factor. But they were making, sub-polynomial savings. So polynomial loss is not going to hurt as much. And from this, I can immediately get all the things. So does this make sense? So this is the key main result that I wanted to tell you about. There is a clean two-server protocol using derivatives. There's one little bit of a trickery. What did we do really? So the general idea is we are going to consider the composite numbers that we were looking at. We can look at it, we're going to look at it in a special way. The composite is going to be of the form m times a prime p. And we will work over a field which is of characteristic p and has an nth root of unity. It's not a big restriction. You can always find such a field. So it's not a big deal. In our case, we happen to, when we used m equal to 2 and p equal to 3, q equal to 3 worked for us. But if not, we would have used a slightly larger field. And once you have that, you get the identity that z sub m to the p is really this guy. And so you can get up to p derivative informations from any one query. This will blow up the amount of communication by a power of p maybe, but we don't care so much by this constant factor loss. But on the other hand, we can basically get whatever you were doing with factor, the number of queries that we are making becomes much smaller. Okay. So far, we got rid of the sparsity consideration and put in something else and worked with this, and it worked well. Okay. So this is where, by the way, this is all was done before I even joined this team. And so Swastik and Fatema already had this.
So if MP was 6, you're still going to use the BBR matrix. The matrix is going to be used.
Matrix is going to be the same. And as far as I know, there's no better technology for building nice matrices. And also, there's no nice technology for how to characterize the sparsity of decoding polynomials for various S's. I mean, both of them went ingenious in one direction or the other. The BBR construction for matching matrix and Ekanen for the sparse S decoding polynomials. These things we still don't know how to do any better than them, but at least given these two ingredients, this seems to be the best way of doing it. Finally, there is this thing that we said, oh, look, all these sparsities and so on were showing up in various places, right? I mean, Ekanen was using it crucially. And we didn't like sparsity, but it turns out that there is a nice way of interpreting sparsity in our setting. What does it mean? We know that our polynomials that I'm looking at, this polynomial little g, its monomials were of the form t to the s, where s was an element of capital S, right? Sparsity, what they used it for was to translate it to say, if you want to interpolate one of these polynomials, of course, if you want to interpolate and find all the coefficients, you have to at least ask as many queries as the coefficients. But if you only want the 0th coefficient, it suffices to find some sparse polynomial doing blah, blah, blah. Our interpretation is, if you want to find only the 0th coefficient, you can evaluate it at number of points equal to that sparsity. So there are some key set of locations where you ask the questions, and then you'll get back the thing. So sparsity turns into query complexity of how many queries does it take to compute the 0th coefficient of t to the 0 in a given polynomial. And once you see it this way, this becomes, all the previous results kind of fall into this framework. And not only that, we get the power to use multiplicities. And so, if I can evaluate if I'm just evaluating some previous polynomials, maybe I can also evaluate them and their derivatives. Does that help? And it works seamlessly, just perfect melding of the two. There are a couple of lemmas that tell you all of this. This bonus lemma is not something that I managed to, completely spell out in this slides, but you can take a look at the paper. It's the lemma 4.4 over in the paper. So that's the summary. We have a PIR scheme which is getting really good performance. So in particular, if you decided to do a 2-server PIR with this, we will get the Dvir-Gopi result, exponential square root of log k. We can also get a 3-server PIR with communication exponential and cube root of log k. And this is the first such improvement for 3-server PIRs.
Also, the number of servers different. I thought from LDC to PIR, you had a drop in the, so why did that happen? So you said a two per R query LDC gave you a two per R minus one.
Morally,
So where did,
so when you're looking at, so where is the number R? I'm thinking of my number M as a product of R distinct primes.
yes,
Then where is what does the BBR construction tell you? It says that, look, you can get, 2 to the, this N
let's
can
actually fix to Z6.
Z6. Okay.
The
So
LDC that you get there will be a 6 query LDC.
the vanilla one will be a 6 query, but we just improved that to it, and we turned it into a 2 query, 2 server PIR, right?
Yeah, how did you turn it into 2 server PIR?
That was this thing here,
The
right?
6 queries are the value and the 2 derivatives.
Oh,
So
okay.
you ask to server this value and derivative, this value.
So just, using many derivatives gives us this thing. And in general, when you're looking at the product of R composites, one of the composites you can just take to be the new prime field that you're going to work with, or the characteristic of the prime field. So you can get its derivatives with respect to one of the primes, and that makes sure that one large component of the set of residues that you have to work with in S goes away, halves the size of the set S effectively, and so halves the size of the number of queries that you have to make. So yeah, that's morally where it comes from. Okay, so there are a bunch of questions, but how, good technologies for building matching matrices, and actually matching matrices, of course, there's this wide open question of, is this the best possible? Can you do much better? If this is the best possible, how do you ever prove a lower bound? It's a very concrete question, and I don't know how to think about it. Going from a set S to what's the sparsity of the decoding polynomial, or what's the size of this interpolating set, I don't know what it is. And so far, no, we prove results which use multiplicity 2 typically, and are things are strong enough to give you much larger multiplicity if you want, but we don't know how to use it really. I mean,
puts more communication on the question,
yeah, it'll put more communication into the answers, rather than the questions. But it's only polynomially more, but we don't know how to take advantage of the many more things. I mean, so the BBR construction, for instance, it says, look, of modulo every prime, I will either use the option of being 0 or 1. And this gives me lots of benefits. That's 2 possibilities. This translates to basically 2 derivatives is all we need. So we never are able to use more. Right, I'll stop here.
Further questions?
I had a couple of questions. So one is, so you're saying multiplicity 2 here, does it mean P equals 2 in the best parameters you get?
No, P is not necessarily 2. We
felt
just
like the scheme you described. There was this going mod P, going mod Z minus 1 to the P outside. This thing. So it feels like you can go up to multiplicity P in this. Because you're going mod this.
Exactly. So we can go up to multiplicity P, and it would cost us almost nothing in terms of the communication complexity. It's the power of P.
You work with lower multiplicities even when you could go to higher.
Yeah, the thing is, these residues, set of residues that you find, the set capital S, uses this. So the way to look at the set of residues is always, what does it look like modulo each one of the primes that's dividing it? And it will take on 2 values mod every prime. So if it was taking more values, that would have been nicer, and could build some larger matching vector set. That would have been nicer, but we don't know how to use it at all.
Second question was, so just trying to understand where the gain really comes from. So it feels like in these lopsided schemes where the forward communication is more expensive, the cost is really in these matching vector construction, the dimension on top. These are matching vectors in how many dimensions?
Right.
So that's sort of the bottleneck in the vanilla matching vector based constructions.
Right.
So our goal would be to construct some n capital n matching vector families of size n, where n is the number of bits in the message we want to encode. And we would like to do this in lower dimension. And one way of doing it in lower dimension is sort of to work with a modulus which has more prime factors. And going from little m to little m times p is like you're gaining one prime factor in the modulus. This lets you bring the dimension down a little bit. The decoding becomes more complex.
Right.
But is this where the
This is where the advantage is, but really the way I would think of it is different. I would just say, look, think of a scheme that you have which uses this many things. So each server is basically sort of taking care of one residue possibility for every prime. So modulo, if I'm taking the product of P1, P2, and P3, then this server will take 0, 0, and 0, and that one will take 0, 0, and 1, and this and so on. We're getting rid of one of these composite classes by saying, okay, like let's get rid of the last prime and instead ask each one of these guys to report enough derivatives
higher
to take care of. So the 000 server and the 001 server got merged into one, and we're saying, oh, look, now you just doing the job of both of these servers, so tell me a derivative also. Does that make sense?
Yeah.
So and we always knew how to use more servers to get less communication.
Question. So right now you're using the fact of ZMP minus one factorized in ZM minus one P. And this sort of takes the multiplicity codon. Suppose this it factorized not into ZM minus one, but Z minus A, Z minus B, Z minus C factored somehow this way. Can you do like sort of like a multivariate folded Reed-Solomon code? There's one place where I see the proof breaking down in this because then you have more scope for only places you're using multiplicity in other sense. And if I have multiplicity in M fixed directions, you can also find multiplicity in a specific direction. Multiplicity codes have this extra feature. Folded Reed-Solomon don't have this sort of folded Reed-Muller won't have this feature. But this gives you a little more flexibility if you can allow for arbitrary factors rather than roots of
Right.
you know.
But really, I think what we cared about is this factorization, not so much that one.
No, but
This is what we see. And then we really want, so if you can write it as a product of a bunch of things, each one of which is raised to a moderately high power, along with the feature that the information that I'm interested in is also, I mean, so yeah, I mean, so these should be factors of the polynomial that I care about.
So it doesn't have to be Z plus one to the whole cube. No, it could be
If it's Z plus 1 times Z plus 2 times Z plus 3, and it doesn't help me. But it doesn't have to be cube here and cube here. It could have been 2 and 4 there. It would have been okay. That
no,
would-
I'm claiming Z plus one and Z plus two plus Z plus three is like you're giving.
you could ask one of the servers for Z plus one.
You give like a
mod
folded
Z
Reed
plus one
Solomon code. You
times
give it
Z
as
plus one.
f of x, f of gamma x, f of gamma square x, hoping that these will actually be these, and hope to recover from that. And I'll ask this. I'll need to formulate the question properly. I can ask.
yeah, maybe. I mean, but I don't. Yeah, I don't see the ability. I don't know if we have like if we can go in the folded Reed Solomon ways from multiplicities. I don't know. Yeah, I don't think so. But good question. Yeah.
Any other questions?
Okay.
Let's thank Madhu again. I have a question, but turn off the.